point.
Okay.
Not here. In Teams.
Here.
You go to share
Windows.
content. Yeah.
Okay, in Windows.
If you have multiple screens, they will show you screens.
Okay. Now I guess the full screen is
No,
have
no,
seen.
no, no, no.
Shit.
Let's keep it.
Interest for time, maybe just carry on as is.
Yeah, yeah. I mean, if it's visible properly, I can move further with this. Oh,
Your sharing has stopped now, so you need to reshare.
okay. Okay.
Yeah,
The
now
screen
it's called. Yeah, now it's perfect.
Now it's
okay.
perfect.
Okay. Let's
Thank
move.
you all.
Okay. Thank you, Jabir.
It's all
So
right.
the
Now we
outline
can.
of the presentation will start with the potential benefit of the waveguide technology. Then we'll move to the motivation behind the reconfigurable filters. Then we will take a look on different approaches of the reconfigurable filter. Then we'll deal with the complication associated with the metallic tuning element, and then we'll take a look on dielectric tuning elements and its benefits. Then we'll move on the experiments we have carried out with the resonator input coupling areas and the inter resonator coupling areas of the filter. And at the end, I'll show you the simulation and the measured result of the recently published, recently designed filters by our team. So let's move to the other slide. As the waveguide technology have the benefit of high rejection, low insertion loss, or high power handling, and it has a high repeatability in term of productivity, and it has a high Q factor. The major reason behind it is with the PCB type of filters, the major material is a dielectric, which have its own losses. But for the cavity filter, the dielectric is replaced by the air, which is somehow the lossless thing. In that way, the whole air cavity is being bounded by the steel, which shield the signal from the interference. That makes the waveguide filter more safe for the low insertion loss and high quality factor characteristics. On the same side, on the other side, waveguide technologies have some cons, as it has very high weight. It's very complex to design a wideband filter more than 30% of bandwidth, and the mechanical movement in for the tuning is highly complex in case of waveguide technologies. So we'll deal with these problem in our upcoming slides. So let's move to the another one. The motivation behind to move the for the reconfigurable filters is, as the payloads have the different channels to communicate in transmit and receive chain. So if we can replace those multiple channel of the payload with a single tunable diplexer or tunable filters, then we can reduce the weight and the cost of the components in the payload. At the same time, we can reduce the complexity of the multi-channel transceiver payload architectures, and at the end we can optimize our usage of the allocated frequency band, which is nowadays is a commodity for the telecommunication engineers. So that's all around the motivation behind the reconfigurable filters. Then we'll move to the various approaches associated with the filters. Like filters can be tuned either by the mechanical methods or by the electrical methods. In terms of mechanical methods, either we can use the plunger to change the cavity size in order to tune the frequency or bandwidth, or the other method can be the use of metallic screw inside the uh, traditional waveguide structures. Another method can be to exploit the capacitive disk in order to tune the COM line type of topologies. Recently, some of the researchers have shown the rotational inserts inside the cylindrical cavity in order to tune the filter. And the latest one, some have exploited the tuning range through the pneumatically actuated liquid metals. These are the all are the mechanical method. Apart from that, there are some electrical commands which can be used to tune the filter, as the MEM switches or the varactor diode, or the some have used the metallic approaches in a ferrite based cavity in order to tune the filters. So let's move to the another slide. In our approach, we have generally dealing with the dielectric or the metallic tuning elements. So there are some complications which we have observed with the metallic tuning elements, as when we tune the filter using a metallic screw, it has to be securely fastened to the body of the filter in order to operate it correctly. That thing make it this method very complicated to for the remote tuning, because it has to be in the contact with the filter structure all the times. One more thing with the associated with the metallic tuning, as this it is very sensitive in terms of the position of the height of the tuning screw. So as we are using some low cost step up motor or actuator motor, so it's very hard to control those type of motor with metallic screws. Use of metallic screw also degrades the quality factor of the filter very drastically. and and the last one is like, when we use the metallic screw, it has very negative effect on the power handling and the passive intermodulation performance of the filters. So that's why we are intended to move to the use of dielectric tuning element rather than the metallic tuning element for our filter topology. So there are some potential benefits of the dielectric tuning elements, which uh, which are like, we don't need a regular contact of a tuner with a metallic body in order to tune a filter with dielectric tuners, which make it very easy to operate with a remotely controlled motors and with a low accuracy. Apart from that, using a dielectric tuners make the structure more compatible and eliminate the common source of passive intermodulations for the while testing the filters. So let's move to the target areas while exploring the tunable topologies. The problem with the tunable topologies of the filter is like, when we move the frequency range, we have to compensate the input output coefficient and the inter-resonator coupling coefficient at the same time in order to maintain the proper response of the filter. So when we are dealing with the resonator tuning, we have to compensate the input coupling and the inter-resonator coupling at the same time in order to maintain the return loss and the constant bandwidth throughout the filter. So in that way, we have carried out our experiment with the resonators, then input coupling and the inter-resonator coupling in order to exploit the tunable range. So let's move to the first step, as these are the uh, traditional rectangular cavities which have a combined topology, and the basic thing to tune a filter is to exploit this capacitive uh, gap in order to tune with the metallic screws. So we had carried out the experiment to see the behavior of the frequency using the eigenmode solvers, and like we can see from this graph, the frequency has been changed as we move the height of the screw. But one thing we have observed, like, this behavior is highly nonlinear, and as we move it further, it's quite steep, so it's very hard to handle with the low cost motors. And the second thing, it's if it's very non-linear, then it's very hard to predict the height of the metallic screw in order to tune something remotely. So in order to deal with these issues, we moved to some steps. We replaced the metallic screw with the dielectric one, and we have seen there was some improvement in in the non-linearity of the sweeping range of the frequency. Then we moved ahead with some more iterations. We have realized like, this type of solid combined post make it very hard to move the dielectric tuner further. So make a more room for the dielectric tuner, we carried out this approach to make a hollow post and try to iterate the dielectric screw from the opposite side in order to tune the frequency of the filter. So this is the uh, range we achieved through this topology, but we were intended to make it more reliable and more linear in order to make more tuning range. So we moved to this type of topology shown in here. We have just uh, switched our approach from this bottom to this one. The bottom wall, the dielectric at the bottom wall has been replaced and located inside the hollow post. It's like at the initial end at 1.85 gigahertz, let's say, the whole dielectric was enclosed inside a metallic uh, enclosure. And if we want to tune it further, we move the dielectric out of the metallic enclosure, and in that way we carried out the experiment from this end to end of the cavity. And here we can see that the whole tuning range is almost linear, make it more compatible to predict the frequency. Like if we want to just remotely tune a frequency of the filter at this one, so we can just linearly calculate our tuning approach. So we move further with this resonator topology to design our filter onwards. The next step was to design a input coupling topology in order to compensate the uh, response of the filter throughout the tuning range. So for this purpose, we use this formula. It's very known formula associated with external Q factor. As we can see here, like if we want to move the frequency to downward, we need a lower external Q factor in order to maintain constant return loss and bandwidth. So we carried out the experiment with some basic input topology, and we can see here also there was some change at the end of the tuning experiment, but the behavior was quite steep, make it more complex to tune the filter practically. So we moved further to the other topology and carried out the same experiment in order to observe the Q external variation with respect to the height of the tuner. So there are two type of topology we proposed. One was this one, in that we proposed a hollow post associated with a coupling, coaxial screw at the input, and we started to insert a dielectric inside this post, and we can see the change in the external Q factor as we move this dielectric screw out of the enclosure of the input post. So in that way we intended to compensate the external Q factor at the lower frequency of the tuning range. At the same time, we switched this post to the opposite end of the cavity, and we carried out the same experiment, and we inserted the dielectric screw out of the enclosure. In that way, we made a large sweep in the variation of the external Q factors. So according to our requirement, we'll use this topology in our whole filter in our coming slides. Then the next approach was to explore the input coupling in order to maintain a constant bandwidth. So we started our experiment with taking this two cavity model, having low coupling on the both side, and we started to insert a dielectric screw in a traditional inductive window, and we started our experiment to observe the coupling coefficient variation with comparison to the height of the tuning screw. So this type of behavior we observed, like when we insert the dielectric screw inside the input interresonator coupling iris, the coupling coefficient has been increased while moving to the lower frequency. So in that way, we propose some other interresonator coupling in order to compensate our bandwidth. Those coupling we have carried out some other experiment with the other coupling topologies, which I have not shown in this slide because like it's still under to be published. At the end, when we had a resonator coupling and the and the independent topologies for the every stage of the filter. We designed a whole 4-pole filter having central frequency at 1.84 gigahertz, and we were intended to tune a center frequency of the filter up to 1.54 gigahertz while maintaining the bandwidth of 75 megahertz, and the return loss, initial return loss was 25 dB, and we are intended to maintain the same equiripple return loss throughout the tuning range. So we started our
1 minute.
Yeah. Yeah. Okay, just so we started our experiment from this, and at the end we were able to tune the filter up to 1.54 gigahertz while maintaining the constant bandwidth. Moving ahead, this work has been validated with the HFSS, and then we moved ahead to design a fully reconfigurable filter topology with our studies, which was able to tune a frequency at the same time. And if we want to adapt a variable bandwidth, we can move our bandwidth to the double size of our initial bandwidth. As you can see, we have designed our filter at 2.175 gigahertz having initial bandwidth of 50 megahertz. These are the measured result we measured with VNA. So we started with this response, and we could tune our filter up to 1.475 gigahertz while maintaining the 50 megahertz bandwidth. And the main thing we noticed throughout the bandwidth, we could observe the insertion loss better than 0.3 dB. And within a same structure, we can double our bandwidth from 50 megahertz to 100 megahertz at 1.92 megahertz bandwidth, and we can tune the frequency while maintaining the 100 megahertz bandwidth up to 1.6 gigahertz. And even though at this stage our insertion loss we could achieve was better than 1.25 dB throughout the tuning range. And the one thing we observed here, like our return loss was better than minus 25 dB throughout the tuning range. And this type of topology provides the user to adapt any bandwidth between 50 gigahertz to 100 megahertz throughout the tuning range. So that's thing we measured recently. That's all we did in last days. If you have any question about my work, feel free to ask.
Thank you, Abhishek. Any questions?